Any questions? So let me see, we saw last time how you can construct tensors. I mean, given some representations, say fundamental representations of some symmetry group, you can construct tensors. And then we also saw how these tensors can be reduced. They're not irreducible representations. They're reducible representations, and there's some systematic way of reducing it to irreducible representations by considering various symmetries. The symmetry group, the permutation group acting on the indices. For example, totally symmetric object will be one irreducible representation. Totally antisymmetric will be another irreducible representation. But then in general, there can be also mixed ones. Now, for SU2, fortunately, we don't need all of that really, because we already directly worked out the spin J1 times spin J2, and we saw how it works. I mean, in fact, for SU2, you see that if you take any two fundamental representation, which is fundamental representation is spin half representation, right? In SU2. So if you take an antisymmetric product of the two, it is going to give you a singlet, right? I mean, we saw that, right? It will be spin 0. Spin 0 means invariant. So if you have now a product of several spin halves, you can talk about various symmetries and antisymmetries, but anytime there's a pair, one pair, which is antisymmetric, then you can just remove them because it just gives you a singlet, right? Because that combination doesn't transform under SU2 because it's a singlet, right? So you can just get rid of that pair, and then what is left over is totally symmetric. If there is still something antisymmetric, you also remove that. So this way you reduce to totally symmetric combinations. That is all that survives. So SU2 is very easy. SU3 is a bit more complicated. So what I will do is, instead of discussing in general how to use this permutation group, first let's go to this SU3. Okay. Then I will come back to it. After describing the SU3, then I'll come back to this discussion if I have time. I don't know how much time will be. So let's today start with the SU3. Young tableau will come back to it after the SU3. Okay, young tableau is just a way of writing. It's a kind of notation for what we already said. Remember, because we said if I let's say Tijk, 3-rank tensor, then we had several possibilities, right? One was a totally symmetric. Then there was another which was totally antisymmetric. And then there were two guys in between, Ijk and Tikj, okay, which are kind of mixed, like symmetric in this, but not in that. No? So there was this mixed thing which we wrote down explicitly, I think, a couple of lectures back. But in the SU2 case, you don't need to worry about anything, because any time, if you look at this, any pair you antisymmetrize, that becomes a singlet. So you can just remove them. Right? So in this case, SU2 case, it becomes very simple. There is a totally antisymmetric combination, okay? Or then there is just I, because suppose I take one of them, this pair to be antisymmetric, you can just throw them out. There is just that. So indeed, you know that spin half times spin half times spin half. This can give you what kind. So let's just do that. Let's just try to check whether this is true or not. So if I, first of all, how many states are there? Okay, let's try that. So here you can first decompose. First, take the product of this. Okay. So spin half will give you spin 1 and spin 0. So this will give me spin 1 plus spin 0, right, times spin half. Okay. Now I take this is a sum, right? Product with each of them. So this is the same as 1 times half plus 0 times half. tensor product. Now this one, this was spin 1 and spin half. And we already know the rule for generally for if I have spin j and spin j prime, it will go from j plus j prime all the way up to j minus j prime. Okay. So this will give me a 3 half, 1 plus 1 half, and then another one would be 1 half. Okay. That is coming from here. And then of course, this was all coming from there. And then I have here 0 times half, but 0 times half is simply half. Right? It's a singlet, that's a spin 1, spin 0, spin half, only possibility is half. So this is all that you get. And in fact, just to check whether you have not missed anything, you can look at the dimension of this. This is dimension 4, right? J plus 2j plus 1. J is 3 half, so 2j plus 1 is a 4. So the dimension of this is 4 of the first guy, 2 of the second guy, and 2 of the second guy, the third guy. That's 8. And that is indeed the total dimension here, right? Because this dimension is 2, 2, 2, 2 times 2 times 2 is 8, right? So that is I mean, if you're given some problem like that, it's always good to check, because sometimes you might miss something. So that's a double check that you have not missed something. In any case, SU2 is very simple. I mean, you already have a general rule for any spin j and spin j prime. So then you can just keep repeatedly using that and get all the representations. SU3 starts becoming more complicated. So maybe after discussing SU3, we'll come back to this. Okay, so with this, let's start the SU3 discussion. Yeah. So SU3 is the group. SU3 is 3 cross 3 unitary matrices with determinant equal to 1. So in general, SUN is an n cross n unitary matrices with the determinant equal to 1. So this SU3. Right? So that's at the level of group. At the level of Lie algebra, I don't know, let's say SU3. Lie algebra, what it would be? It will be 3 cross 3 Hermitian matrices, Hermitian or anti-Hermitian depending on your convention. Hermitian matrices that are traceless. Right? This we have seen many times, right? The unitary matrices, if you look at the infinitesimal version, it is Hermitian matrices, right? When you write the matrices as so some G as identity plus some X, small x, then if this is unitary, then X must be Hermitian. Okay? Sorry? Anti-Hermitian, if I put an I should put an I there, correct. Yeah. So yeah, otherwise it will be, if I don't put an I, it will be anti-Hermitian. Right? So if I look at this, I mean, usually in physics literature, you always write it in terms of Hermitian, although there is no particular reason. You could absorb I inside, and it will be anti-Hermitian. And this determinant equal to 1 condition gives you the tracelessness. Okay? So let's write down, in fact, let me just write down all the matrices here, somewhere here. These matrices were, this is, you have to choose it. Okay, first of all, let's see how many such objects are there. Hermitian matrices, 3 by 3 Hermitian matrices will be 9 of them, right? Okay. Because, I mean, if you have a 3 by 3 matrix, Hermitian means diagonals are real, right? And off diagonal guys, whatever, so you have 3 off diagonal here, and they're transpose, right? But Hermitian means if I tell you what this number is and this number is fixed, it's just a complex conjugate of that, right? So you have 3 real and 3 complex, that is altogether 9 real, right? So 9 real, but then there's a tracelessness condition, that is sum of these 3 is equal to 0. So out of these 3, only 2 are left over. right? Because if I tell you what are these, then this is fixed. Traceless secondary. So then it's 8 of them. There are 8 traceless Hermitian matrices. Okay? And this was a basis that Gell-Mann introduced. And I think he was probably the first one who started using SU3 groups for particle physics. You know, he wanted to classify certain the known particles at that time. You know, essentially the particles which are known were these mesons. Apart from the protons and neutrons and so on, if you look at the mesons, what was known was all these pi mesons, k mesons, etc. And he realized that if you ignore that, there are of course mass differences between them. They are not exactly the same mass, but small differences. So suppose you ignore the masses and the charges. They are all different charges. For example, there are 3 types of pi, right? Pi plus, minus, and pi naught. These are positive charge, negative charge, and neutral. And similarly for k, you have k plus, k minus. There is 2 types of k, neutral k. And then there's another particle called eta, okay? Charge 0, it's a charge 0. So there were these particles, and you see the number of these particles is exactly 8, right? So of course they're not exactly the same, their masses are different, their charges are different, okay? But he said, okay, let's ignore those differences. Because after all, charge is a property of electromagnetism, okay? But he was interested in nuclear forces, strong forces. So he said, okay, let's ignore electromagnetic force and also the mass differences. Then there was you could put them in a nice pattern, this what is called octet pattern. There are 8 particles, and that's exactly corresponds to this SU3 adjoint representation. So there was some SU3 group acting on these 8 of them, okay, in the adjoint representation. So this is what his original motivation was. That's how this groups were introduced in the particle physics. Apart from, of course, gauge theory. Apart from that, the most very important thing was the gauge theory, non-abelian gauge theories. That you will study in the next semester, I think. Well, already this semester probably you will see in particle physics course. Alexei will be talking about different interactions and but in detail in terms of the quantum field theory, constructing quantum field theory out of this thing you will study in the next semester. Yeah, perhaps I should just mention here, the reason why I'm distinguishing between these two, both are SU3. The strong interactions. Strong interactions are the ones which are responsible for the quark confinements. The forces between the quarks, which are so strong, they're much stronger than electromagnetic force. And that is what is responsible for confining the quarks. So this is the SU3. Color is, I should distinguish between that, is called color symmetry. Okay? It's just a terminology, there's nothing to do with the color, okay? Symmetry. But Gell-Mann, when he introduced SU3, it was not the color symmetry, it was what is called the flavor symmetry. Okay. So there are 2 different SU3s, although it happened to be the SU3, both SU3. But one of them is a gauge symmetry, other is a flavor symmetry. And flavor symmetry means it's a global symmetry, meaning whatever transformations you make, you should do the same transformation at each space-time point. You cannot do that. At one point you do some transformation, at another point you do different transformation, Whereas when you talk about gauge symmetry, the symmetry is much bigger. At each point you can independently do the transformations. So that's gauge symmetry, whereas this is global symmetry. There are 2 different types of symmetries you will see. I don't know, maybe again if I find some time, maybe one of the last lectures I can just mention something about the gauge symmetry. Although you will study it in much more detail next semester. Okay, so Gell-Mann introduced this matrices to study this the symmetry, the SU3 flavor symmetry, but we will not go into all that. Just look at this basis. It's a convenient basis, although okay. So it's written here. I don't know whether I should write it. 48, in page 48. But let me just, do write it in here. So lambda 1, which is 0, 1, 1, 0, 0, 0, 0, 0. Lambda 2 is 0 minus I 0, I 0, 0. Lambda 3 is 1 minus 1. Is and then here lambda 7, which is 0, 0. And finally lambda 8, which is 1 over root 3, 1, 1, minus 2. These are called Gell-Mann matrices because he introduced them. Now, this forms a basis. Of course, you don't have to. You can choose any basis you want. Basis will have, of course, eight matrices. This is if you look at these matrices, one thing you immediately notice that if I just look at these three matrices, lambda 1, lambda 2, lambda 3, okay, they are exactly like our SU2 polymatrices, where the third row and third column are all set to 0, right? And in fact, if you look at their algebra, I mean, if you take commutation relations between these three, you see that they close here, right? This commutator of these two will give you some number times that, right? And similarly, this with that will give you some number times that, and so on, right? It will never give you the other guys, right? So this means that if I take lambda 1, lambda 2, and lambda 3, these three generators form a subalgebra. They generate a subalgebra, okay? An SU2 subalgebra, in fact. So this generates an SU2 subalgebra. So, of course, I mean, whatever you have studied for SU2, you can, of course, apply to these three generators, right? But what about the remaining guys? Now, if you look at the remaining guys, now lambda 8, by the way, this lambda 8, the way Gell-Mann chose this matrices, you can check that they satisfy a nice condition, trace lambda I, lambda j, lambda I times lambda j, take the trace of that, not commutative, I mean, this is a product, equal to, is proportional to delta ij, and what is it, is 2 times delta ij. Again, it's not necessary, you don't have to, you can just choose any basis, it doesn't matter, huh? But it's just that it happens to be convenient. And we will see much later why this is convenient. That is the reason why he chose this. This looks a very strange. You see, everything else was nice because only 2 entries were non-zero. But if you look at this guy, this and that, this is like the two polymatrices sitting in the bottom block, right? First row and first columns are 0. So you have this like sigma 2 here, sigma 1 here, right? But sigma 3 you don't see, right? But that is simply because one has chosen this basis, this and that. If you look at the diagonal guy, you have this and this. You have this because, of course, this condition comes from the tracelessness condition, you see. So what he wanted to do was, if you choose this for lambda 3, and I want to have something like that, orthogonality condition, then the second diagonal matrix must have equal entry here, right? It must be the same number here, because when I take so look at lambda 3, lambda 8, product of that. So this one is 1, minus 1, 0, 0, 0, 0, 0. And the lambda 8 is 1, 1, minus 2, with everything else, all diagonals 0, right? I mean, why is it 1, 1? Because if it was something different, suppose 1 and x, okay, then when you take the product, the trace will not be 0, right? If you take the product, what will it be? Suppose I call it x here. Let me just call it x1, x2, x3. It should be some diagonal matrix. I'm looking at diagonal matrix. Trace has to be 0, so I suppose I can put x3 equal to minus x1 plus x2, right? Now if I take the trace, product first of all, and take the trace of it, trace. I mean the diagonal matrices, when you multiply, the diagonal elements just multiply, that's all, right? So you will get here x1 minus x2 and 0, right? Because this times that is 0. So the trace will be x1 minus x2, okay? But he wanted to make them orthogonal to each other with respect to this trace. That's why he chose x1 equal to x2. So that's why he made it 1, 1. But if it is 1, 1, then this has to be minus 2, right? Minus 2. And why 1 over root 3? Because he wanted to also get this normalization, right? If you take the square of the lambda h square, you'll get 1 plus 1 plus 4, 6, divided by 3, root 3 square, 3, which is 2. So that's the reason why, yeah? That's the reason why we did that. But there's no particular reason. In fact, from our point of view, it is better to take some other basis. Instead of lambda 8, we can choose this rather complicated basis. What should I say? So for example, I could choose lambda 3, root 3 lambda 8 minus lambda 3, okay, divided by 2, maybe minus that. Because if you do this, I think you will probably, if I have not done a mistake, you should get this object. That particular combination. Okay, you can, I mean, root 3, so this goes out, you just that. This minus that, so the top guy cancels. Here you get, so there is no minus. Yeah, here you get 1 plus 1 minus minus plus 1, 2. So 2 minus 2. But then I divide by 2, so you get that, right? Similarly, I could have chosen another. Okay, now if you choose this one, in fact, I don't know what should I, let me call it H3. Let me just call it H3, that particular combination. Then you see that H3 and what is it, lambda 7. So you see that lambda 7, H3 and lambda 6, they will again form an SU2 subalgebra. You see, because now the H3 is this one, right? This guy, and that guy will again form an SU2 subalgebra. This is like the polymer. First row and first columns are all 0 for all the 3. And you can just focus then on these 2 by 2 blocks, right? And the 2 by 2 blocks, there is polymatrices. So that will be again another SU2 subalgebra, right? Similarly, now look at the remaining guys. This 2. So here, if I consider now another combination, which is probably, let's call it H4, which is 1/2 root 3 lambda 8 plus lambda 3. Because now if I take the plus, then this guy cancels, okay, and you get 2 minus 2, okay. So this matrix will be what? Will be 1 0 0 0 0 0 0 0 minus 1. This will be the H4. And that H4 now together with H4 together with lambda H4 together with lambda 4 and lambda 5 will form another SU2 subalgebra, right? So you see there are lots of different subalgebras, SU2 subalgebras are there. But it's not that these different SU2 subalgebras commute with each other. They are not. Okay? So it's a rather complicated way of embedding these SU2 subalgebras inside SU3. But they don't commute with each other. For example, let's look at this SU2 subalgebra and let's look at this SU2 subalgebra. Now, and if I look at the commutation relation, so we have lambda 1, lambda 2, lambda 3, that's one of them. And say this, and that H3, lambda SU2 subalgebra. Now if I take the commutation relation of this with, for example, that, It is not 0. So that is so important to realize. It's not the direct sum of these 3 SU2s. It's rather complicated. Each SU2 is inside the big SU3. However, this will help us to really understand completely SU3 because we understand SU2 very well, right? So the idea is to think of SU3 in terms of the subalgebra. Take one as the SU2 subalgebra, right? Try to understand how the other guys are. So suppose I take this SU2 subalgebra. Then I want to understand how under this SU2 subalgebra the remaining generators transform. Can I group them? You see, everything has to be a representation of SU2. You understand? I mean, you have this big adjoint representation, which is 8-dimensional representation, right? Inside that adjoint representation, I have the adjoint of this SU2 subalgebra, right? But when I look at the computation relations of these with the remaining generators, they will be not in the SU2 adjoint, but it will be some representation of SU2, right? And we know everything about all representation of SU2, and that is what will help us to understand SU3, or in general any group, any Lie algebra. So this is the idea. Okay. Although many times I'll be using this this kind of these H's, these combinations, but we'll see that it is. Remember I mentioned to you the reason for this choice was that you wanted to make trace lambda I lambda j is proportional to delta ij. Okay, in this particular case I think it was 2, but it doesn't matter. More important is proportional to delta ij. In fact, this trace can be thought of as a metric in the space. That this we will see later. It can be thought of as a metric on the Lie algebra. You have chosen a basis, so this is like I don't know some Gij, a metric. Okay, this can be thought of as a metric. So with this choice of basis, you have taken the metric to be just Euclidean. That's why that is only advantage of that. But otherwise, it's not important. We will study the metric later when we discuss, not in SU3 context, but when we generalize it, we'll introduce a notion of killing form, killing metric. Okay, that we will discuss it later.
Is this property changes does it affect adjoint representation too?
Sorry.
Is this property would be different?
Which property?
The metric, as you called it, would be different. Is adjoint representation going to be affected by it?
No. You see, this is a basis. Adjoint representation is defined for the entire Lie algebra, right? This is choice of basis. This to give an example. Suppose I have a Euclidean space x, y, z, right? Where the metric is simply all the x, y, z.
Doing this way, we make all matrices orthogonal to each other. In some
not really.
sense of orthogonality.
Not really. No, it's not. No, it's okay. Yeah, okay, fine. But yeah, that's okay. But it's like choosing x, y. Say I have 2 dimension x, y, right? I chose it's perpendicular, orthogonal. But I could have equally well chosen another basis like this. No, this is my x and that is y. Now these are not orthogonal. It doesn't matter.
Yes, but when we go to the adjoint representation, we saw that they act like Euclidean basis and we can rotate it like SO3. Maybe that property would be affected by if they are not orthogonal.
There we didn't even choose a basis. You see, there we said an arbitrary G, right? When you look at the adjoint, the way it acts on the adjoint representation, you have some 3 by 3 matrices.
Results.
Yeah, 3. There was no choice of a basis, right? This is a choice of basis, nothing big deal about that.
Nothing will be affected by
nothing
if this is satisfied or not.
Yeah. It becomes convenient though, not to draw pictures. We'll see that in this basis, if you try to draw some pictures that we'll get.
When we have chosen Pauli matrices by half would be mapped to the new generators in SO3, that was a choice. So that kind of choice is somehow connected to that.
If you choose instead of Pauli matrix, choose some other combination, they will go to some other combination.
Other combinations will go to some other.
Right.
But when you explicitly calculate G polymetries times G
Yeah.
inverse, which we do in the other lecture.
Right.
To show it works like a rotation, we use especially this property. So this works to show that it is actually a SO3 rotation in polymetries sense. Somehow it works to show it, but it's all depends on the choice.
Yeah. I mean, there is no fundamental, there is no issue of principle based on this. Basis is just a basis. I mean, because different people can choose different bases. Shouldn't matter. Results shouldn't matter. Okay. So now, so let's see. So how to proceed this further? Yeah. Okay. So certain things you can check. I don't want to go through all these checks here. Maybe I should also introduce that. Okay, so let's see. I should just introduce one notation, which we will be using later much more. All of this matrices, instead of writing this huge things, I mean, fill up the blackboard writing these matrices, it is convenient to choose a basis. So choose a basis. This is just a notation. Again, no principle, no deep thing inside here. You choose a basis for, say, n by n matrices. And this basis will be Eij. Okay? So this is notation, Eij. What is a n by n matrix? But it has how is it defined? It is defined such that this is, so this is n by n matrix, where the only non-zero element, everything is zero except the element which is in the ith row and the jth column. Okay, so this guy, here you put a 1, and here you put a 1, this ith row and jth column, and everywhere else 0. Okay, you can. Right? So this is a basis, of course, because so how many basis vectors are there? I goes from 1 to n, and j goes from 1 to n, right? So I mean, so you have n square basis elements, right? So it's clear that any n by n matrix I can expand on this, right? Any n by n matrix I can write it as some alpha ij, eij, where alpha ij is numbers, summed over I and j, right? So this just means alpha ij is the entry in this matrix M. Alpha ij will be the entry in the ith row and jth column. This is a way of writing. So in this way of writing, you see that we can immediately see that lambda 3 is simply E11 minus E22, right? The fact that it is traceless means all the matrices now will have the property that sum over alpha I will be equal to 0, right? That sum over alpha I. Okay, this is just a notation which we will. I don't think we'll use it very much here, but maybe later on when we generalize it, we'll probably use it. Because clear for, I mean, 3 by 3 matrices you can still write on the blackboard. If you have large matrices, it will be difficult to write. Okay. Yeah, and you can, of course, also construct the Lie algebra. I mean, in this basis. In this basis, you can, I mean, this I will not do. It's just a matter of directly working it out. So you can, so yeah, so in this language, then what I was calling, I don't know, I mean, those two generators which I wrote down, those two combinations, I wrote down, which was, I don't know, root 3, lambda 8 minus lambda 3, 1/2, and the one with the plus. Root 3 lambda 8 minus plus lambda 3. These were just, I think, E22 minus E33, this one, and this one was E11 minus E33, right? So instead of writing all that, you could just that. Okay. Given, I mean, this Lie algebra, so what is the Lie algebra? There are this, of course, the vector space plus together with the commutation relations. So you can, so in general, so if I choose some basis, like for example this one, I can look at this computational relation lambda A, lambda B. Whatever it is going to be a linear combination of again these objects, right? So I will write it like this. Since I am choosing Hermitian, a commutator will always be anti-Hermitian, right? So I have to put explicitly I in front, right? So it will be some F, A, B, C, lambda C, right? Where again repeated C is summed over. A and B is just to keep track of the fact that, I mean, these numbers will be changing if I change A and B. You know, different matrices when I take the commutation relation. So is that. But of course I know one thing, that it is antisymmetric in A and B. Because lambda B, lambda A commutator will be a minus of lambda A, lambda B. So this, whatever this FABC is, it must be that it is antisymmetric in A and B. Okay. These are called structure constants. Structure constants. Structure constants of the D algebra. In this particular, for this particular choice, you can easily. Oh, by the way, I don't know. Yeah, we have put here half. I don't know why. Okay. Instead of choosing this as the basis, we have chosen half. But that is because, like H, remember already for SU2, they were taking sigma 3 by 2. Okay. But again, it's not important. All that, if you had not multiplied these things, okay, these numbers will be multiplied by some factor. That's not again important. Now, in this, for this choice, all the FABC are given, and please check that. This is given in page 49. For example, F1, 2, 3 is equal to 1. Page 49 is below 8.21 equation. You know, here, if you have the, so it's all written there, numbers. So please check that, there could be also typos here. 147 equal to half, and so on. Okay? So all these are given. Okay. Now these ones have a rather interesting property. Incidentally, again, yeah, I should. Okay, okay, I'll comment on that. In the lecture notes, it's, C has been put here. Okay, down. But it's more correct to put it like that. However, it doesn't matter because of this fact here. If it was not proportional to delta ij, then it does matter. So that is why, okay, at the moment let's just leave it like this. So what you can show is the following. So suppose I now take the trace of the commutator lambda A, lambda B with lambda C. So this is a 3 by 3 matrix. Multiply that by this 3 by 3 matrix and take the trace. Now, if I use this formula here, what will I get here? This will be trace of I, F, A, B, C. These are numbers, so I can take them out. So I, F, A, B, C. Well, so if I 2 times 2, that means 4. 2 times I, F, A, B, C. Right? Good. I mean, you just multiply by 4 both sides. So this 2 disappears. That 2 disappears, you get a 2 here, 2i FABC. And then you get, so this will be equal to, so lambda C, FABC, FABD, let's say, lambda C. And I have to take the trace over this. Okay. But now use this fact that lambda A, lambda D, lambda C is 2 delta DC. So you get, this is the same as 4I F A B C. But this tells you one very important thing. You see, at the moment I already knew that this is antisymmetric in A and B, right? But now from here, you see, it should be totally antisymmetric, right? because I mean, if you, after all, what's the difference in the cyclicity? You can use cyclicity. So I mean, this object inside the trace is lambda A, lambda B, lambda C minus lambda B, lambda A, lambda C, right? But I can, for example, move this here, the lambda C here, inside the trace, there's no problem, right? Cyclicity. But that's the same as trace, or even, just take this guy and move it there. Okay, now let me move this here. So you get here trace, lambda C, lambda A, lambda B. Okay, I don't know. Yeah, maybe it's better to do this way. So I move this lambda B there. Okay, lambda B there. Okay. Not in the other one. So lambda A is in the first place. So this is the trace lambda A times the commutator of lambda B, lambda C. Yes? Yeah, so just the trace has a cyclic property, right? So I have a product of lambda B, lambda A, lambda C, trace of that. I can move the lambda B cyclically around, right? So now it became lambda E, lambda A, lambda C, lambda B. So if you look at these two terms, lambda A is common in the first place. Then you get lambda B, lambda C minus lambda C, lambda B, which is the commutator. Okay. So you see that this object is also antisymmetric in B and C. In this expression, I already knew it's antisymmetric in A and B. But now also it's antisymmetric in B and C. And similarly, you could have moved another way to obtain its antisymmetric in A and C. Okay? So it is a totally antisymmetric object, FABC. I mean, more generally, this happened because we are using this metric here, right? We are using this metric. If not, more correct thing is to to keep this index up, and in that case, you will find here FA. So this is lambda D. So FAD trace lambda D, lambda C. Lambda D, lambda C now is not necessarily Kronecker delta. No? It could be anything. I call it GDC. It is symmetric, obviously, as a metric should be symmetric. No, GDC. I mean, okay. One is assuming that this is invertible. To call it a metric, one is assuming it's invertible. Okay. This is a property of all the semi-simple algebras, and those are the only algebras we'll be studying here. So for us, it will be always non-degenerate. So it will be a metric. And then what this thing would say is that you can use this metric to lower this index, and then when you have lowered that, then it is totally antisymmetric. That's what it is saying. As it is, I mean, if the one index is up, there is no concept of a symmetry or antisymmetry between that index and that index. In order to talk about symmetries, you have to bring it down, right? And that is done by this metric. But since for this case it's just a Kronecker delta, so you don't care. You can just put it down. Okay. In fact, this metric is more or less what is called the killing. It's not exactly that, but okay, it's almost killing form, which we'll be discussing later. It's not exactly that in general, but for the kinds of algebras we'll be talking about, the killing form is proportional to this. Okay, so it's still okay for the algebras we'll be talking about. Okay, so this is a very fundamental property. Then the other property, which again I think you already have seen it. You have already seen that, but let me just this I shouldn't erase this. I should keep it for the time being. But is there any question here? No, I wanted to know, the next point was to show that these structure constants can be thought of as, I mean, they are basically, you can construct their joint representation in terms of the structure constants. This you have already seen it, I think, in a general way, right? I was telling you that, I mean, in general there are many representations, But given an algebra, a joint representation comes for free, meaning it just, from the definition of the commutational relation itself gives you a joint representation. No? So that's exactly what the structure constants will very explicitly give you the matrices for the joint representation. In this basis, of course, when you write a matrix, it's in some basis. No? So in this particular basis, I mean, once you have chosen this generator, some basis, then structure constants are of course defined in that basis, right? And in that basis, you can write down the adjoint representation matrices. And the way it works out, can I erase this part now? All of that part. I just want to leave that here. Sorry. By the way, when you go through these notes, if you find some typos, and I'm sure there are many typos, okay, so please let me know. Maybe make a circle or something and let me know, because we should correct them actually. There are quite a lot of typos here. Okay. So now again some notation. So one of the fundamental property of the Lie algebra was that, of course, it has a commutation relations, but these commutation relations also satisfy what is called the Jacobi identity, right? That was, of course, for the matrices, it was automatic, right? But let's see, you have the Jacobi identity. What I want to say is the following. You see, I mean, you may think that, I mean, if I give you some generators, TATB and FABC, TC, let's say IFABC, TC, that you could have just chosen arbitrarily anything. Of course, it has to be antisymmetric in A and B, right? But apart from that, there is not much restrictions on this, no? But that's not quite true. It's a Jacobi identity which puts restrictions. Okay? And in fact, there's just a simple example given here, which is just to illustrate that you couldn't have just dreamt of some structure constants. No, it need not be. Accidentally, it could be correct, but generally it would not be. So, for example, this is my example given. Imagine that I have 3 generators, and the relations I give is y, x, y, z, 3 y's. Okay. And the commutation relation I give is this: x, y, z equal to x, x, y equal to x also, and zx equal to y. Okay. So somebody suppose gives you this algebra, okay. And then you have to check, of course, whether it is Lie algebra or not. I mean, he's not saying that whoever gave you is not saying that these are matrices. I mean, it is some vector space, x, y, z are some elements of the vector space, and they satisfy this algebra. Is it possible? I mean, is it correct? Well, it has to satisfy the Jacobi identity. That's a crucial thing. So in other words, x, y, z plus, cyclically move around, z, x, y, plus, again, y, zx must be 0. That was an important condition, which we never bothered about because all our algebras came from matrices, and matrices automatically satisfy this.
Yeah. Or at what point?
Sorry.
At what point did we need this condition? Extra.
No, that's a definition of the algebra. The algebra is defined.
The algebra should.
Yeah, it has satisfied. But we never checked it because all our algebra so far we considered are coming from matrices, and for matrices this is automatic, this property. That's why we never checked it. But here somebody just gives you this algebra. You don't know it's coming from matrices or not. Could be some abstract operators.
Is there a particular reason to put such a condition? Is it useful because it's there, or is there any?
No, it's you can obtain these relations. This relation is essentially the same. I think I mentioned in the very beginning when we were discussing from group 2 Lie algebras. Associativity of the group product. Yeah, this translates from if you look at the associativity product and see what happens at the infinitesimal level. This is the
So can we say that if the group is a group is associated,
yeah.
Then the algebra of that group should
satisfy that. Yeah, precisely.
We couldn't.
We couldn't. Yeah. It is not coming from any. It's just coming from the group, and group has some properties. You go to the algebra, infinitesimal generators. They should have these properties. Yeah. So now, if I look at this here, let's just check. YZ is x. So this guy is x with x. But x with x is 0, right? So this one is 0. xy is x, which is xy is x, so which is zx. Okay, and the last one is zx is y, but that's also 0 because zx is y, so y with y is 0, so that is 0. But on the other hand, zx we are saying is y, so this is 0 plus y plus 0, which means y, and that's not 0. So just so, I just wanted, this example is just given to say that this condition is in fact quite, it's a non-trivial condition. No? In the sense that if you started with the matrices and you're looking at the matrix commutators, this is automatic. But if you are not, if you're looking at some abstract group, abstract infinitesimal generators, no? You don't know whether you have to check it. You have to check this property is satisfied or not.
For elements more than 3, how much there is?
Oh, there will be many commutators then. So suppose I have a W also, then I have some W. So you have commutators with W, something here, Y, W, and Z W. So you will have several possibilities.
So for an 8 matrix is how much?
Sorry?
For an 8 SU3.
Yes, no, you can see that. You have to take a pair of 3 different guys, no? So if I have, it's a matter of how many ways you can pick 3 different guys from 8, no? Which is a combinatoric 8C3.
Is there a bigger version where every entry has 8 of?
No, this is all. That's it. Now this is up to this is the Jacobi identity zone. There's nothing more. So if you have 4 of them, then you see you have to pick 3 different ones out of 4. There are 4 ways of doing it. So you'll get 4 identities like that. Okay. So the structure constants, upshot is that the structure constants are not just something that you can freely, just think of some numbers, just put the numbers, just satisfying these antisymmetry conditions. That's not enough. No? It has to be. Okay. So now let's go back to here and see what it does. So if I now look at, let's say, T A, T B, T C commutator. Well, it will be, first let's look at that. So you get here I, F, A, B. Now I should put here some D, T, D, T, C, right? But then I have to again use the same commutation relation. So you get here minus F, A, B, D, F, D, C, D, C, E, right? T, E. Yeah? So I get that. Now you start cyclically moving, because I want to cyclically move this and add them up, and I should get a 0, right? That is what. So that tells me that we have a if I rotate C with A and B, so then I will get another one which will be F C A. No, sorry, what am I saying? D. Sorry, this is D. F C A D, F D B, E T E, the minus sign, and the last one. So this is the T C T A T D, and the last one T B T C T A. So that's going to give me minus. So now I rotate again. So B F B B C D F D A E. Now some of these must be 0, right? But TE are independent. TE is independent set of generators, right? It's a basis. So therefore, we are saying that this implies this equal to 0. This plus that is equal to 0 implies that FABD FDCE plus FCAD FDB DCA, yeah, FDBE plus FBCB FDA E. This whole thing multiplying TE equal to 0, but since TE are a basis, therefore for each TE, for each index E it must vanish, because TE is a basis, no? So therefore this must be equal to 0. That's the condition.
So, what do we mean by the Jacobian identity? Are we mean that we take all the elements of algebra and we reverse them, or we can take any collection of algebra elements and they should satisfy?
Yeah, they should satisfy any
So
three.
the second one.
Any three. Take any three generators.
They
They must
satisfy.
satisfy.
I see. And also 2, 3, 4, any number of.
No, this is not three guys, no. So choose three guys, and then you just do cyclically.
So at least 3 maybe.
This has to be true for any three.
Any 3.
Yeah, in the entire algebra, choose any three. Of course, if any two are the same, then this is a trivial. Doesn't give you any information, right? Suppose, for example, C was equal to B. Okay. Then you see that this guy C was equal to B. These two. So this is vanishes anyway, because if C is equal to B, right? TB will come into TB, of course, right? That goes out. But these two will pick up an opposite sign, because say this is B, then this is TB, TA, that's TA, TB. So if you have only two independent guys, that this identity is a trivial identity. I mean, it's automatically satisfied. But when you have three distinct elements, right? Three different elements, then this is a non-trivial identity. And one must check it. Of course, it is enough to check for a basis. If I have n-dimensional, if I have n such matrices, then I should check for all the n guys, all the three. I mean, every what is it called? Every triplet that you take out from this n, you should check. And once you have checked that, then it's because the rest of it is guaranteed by vector space structure. Because any arbitrary thing can be written as linear combination of this basis. No? This is the condition. Now, you see from here, from this condition, you see immediately that, let me see, I always get confused with this, ABC. So imagine I construct a matrix. So is that clear? I mean, there's no question on that, right? It's just following through this algebra, nothing. Okay. Now, if you think about this, so TABC, right? So let's do the following. Let's call this we have also changed this. There's a bit of a problem in this notes. Because some places we call it structure constants FABC, but now it's written capital C ABC. But please, I mean, just is the same? They are the same. Huh?
Yeah.
So don't. Yeah, it's, okay. So think of this. Let's call FABC as. Think of it as a kind of some matrix defined. Let me not use the same matrix T. Let's call this matrix R. R. There's a matrix for each A whose row and column elements. This labels a row and that labels a column. Think of that. Then you see that this equation is exactly saying the following: RA, now maybe RC perhaps. You should check that. I'm not 100% sure whether there's not a typo here. There could be a minus sign here, I'm not sure. Okay? Please check that. But what we want to check is the following. So maybe I should put something else here. Let's say because A, B, C are the free indices here, right? So I should use some other index here. Let's say Ij, let's say. Ij is Fij. You understand what I'm saying? So these are numbers, right? For each Aij, they're numbers. Now I'm thinking of it as entries in a matrix, right? So I'm calling a matrix R, which is labeled by A. So there are as many matrices as the index A. So if A, B, C take values from 1 to n, for example in SU3, they take values from 1 to 8, right? So this index takes the value 1 to 8. So for each index A, I have a matrix. Okay? This matrix is also 8 by 8 matrix. So I'm just saying that, so if I look at the ith row of that matrix and the jth column, the entry is that. So this is the notation, that's what this notation is. It could be that there is a minus sign here, which means maybe this is IA. You can check. Basically what you want to check is that this relation RA, RB equal to FABC, RC. That's what you should find. Again, there may be some coefficient here, sign or something like that. But this is what you want to check. Okay. So please check this. So I mean, roughly speaking, you see what happened. We are saying, so this will be what? This will be the matrix. If I look at the matrix elements, it will be RA, IJ, RA, JK, right? This will be the JK, IK element, right? I mean, this is the row. And you see, I mean, maybe RB, sorry. RB, JK, right? I mean, just matrix multiplication, RA, RB. So I just take the row and the column, I multiply with the row and add that up, right? It's matrix multiplication. So this minus RB, IJ, RA, JK. That is on the left hand side. Okay? And all of these expressions I can rewrite in terms of F's, right? So what we want to prove is that this is equal to, again, some number here, times FABC, RC. But again, so what am I looking at? I'm looking at here, what is the free, this is a ith row and kth column, right? So this must be ith row and kth column. Now, all of these are replaced by these F's. Then you see each of the term is a quadratic in F. And it should be exactly this Jacobi identity. So that is a kind of, I mean, please check it, because I mean, if I have to do it in the blackboard, it will take me a long time. Okay. So just check it. So what one is saying is that this Jacobi identity allows us to define such matrices, which are, suppose that this number is n, right? The number of this, the dimension of this algebra is n, let's say. So dimension of the algebra is n, let's say. In this case is 8, but anyway, dimension of the Lie algebra is say n. Then these are now n by n matrices, right? And what we are seeing is that we are able to construct an n by n representation, dimensional representation, because this is exactly the condition that a representation has to satisfy, right? Representation has to satisfy that the Lie algebra has to be preserved, right? So this is what. So this is telling you that the structure constants are directly giving you an n by n dimensional representation, which is in fact a joint representation. Okay. It's not surprising because that's how we define the joint representation. A joint representation was just obtained by taking the commutation relation, right? After all, what did we say? Add of say TA acting on something TB was nothing else but the commutator TA TB. Okay. Which in the basis, this is the FABC TC. Okay, okay. So then you see that this is directly giving you a matrix for the TA. So this is the add. So basically we are saying add TA is nothing else but FABC. If I look at the BC element of this, is that up to some sign or I or so on, but that you can check. But essentially structure constant gives you that information. It's not surprising. It's already we have discussed in more generality, right? Now we are saying that when I choose explicit basis, some basis, in that basis, how you can construct the matrices, the adjoint representation matrices. So that was already, I mean, we already knew it. But just check. I'm not sure about the signs. I mean, there may be lots of typos here. But at the end, it should satisfy this condition. Whatever the sign is here, it should satisfy this correct condition.
And these matrices also satisfy to be generated as SO8?
No, these are not generated as SO8. No, these are generated as SO3. So if I want to write down the, they are not going to be, I mean,
it's not like the SO2 with SO3.
no, it's not even SO8.
It might not be SO8, but for some other group, are those new matrices the generators?
Yeah.
So,
Yeah, they will be, certainly, I mean, if I have an n by n matrix, the most general algebra you can talk about is SL and C, no? So all of this will be probably contained in SL and C, anyway.
So some subgroup of SL.
Yeah.
Okay.
SO8, no, SO8. Okay. Now the next topic is the next topic is now. See, remember what we did in SU2. SU2, what we did was we first looked at the Cartan algebra, right? Which was in that case was very simple. It was one-dimensional. It was a set of maximally commuting, mutually commuting sub-algebra, right? I mean, this definition is not completely precise. We will make it more precise later on when we discuss it in general. But for the present case, it's sufficient to say we have a set of Hermitian traces, Hermitian matrices, and I want to look at subspace there, which has a property that it's the subspace abelian, okay, maximal abelian. That's what we did for SU2. So we picked out a sigma 3 from there, right? And then for the other guys, for the remaining guys, we wrote them as some kind of raising or lowering operators, right? So that is a step we want to do now. Yeah. So that will be the next step. Okay, but if there is any question, please. Any question here? It's just a matter of checking it.
Like when you say you have to check it, like to multiply the 1 by 1.
No,
or
just plug it in here. I mean, here there is, I don't know, some sign, maybe some wrong, I don't know. Let's call it X. There's an X, I put X here. This will be,
this should be equal to this.
Yeah, that should be equal to that.
Okay.
So that we should fix the
To
X.
find the X.
Yeah.
Okay.
Good. So let's just start the thing. And then tomorrow we'll continue on that. It is in this sense I was saying that the one representation comes for free. A joint representation comes for free. You don't have to do any work. The moment you tell me what is an algebra, which means defining structure constants, FABC, once FABC is given, you immediately have a joint representation. Okay, so now let's see. So we choose the Cartan subalgebra. Well, it's easy to see Cartan subalgebra. What I mean, maximally commuting. Well, first of all, if I just look at from this set, if I look at the diagonal matrices are going to commute among each other, right? If you multiply two diagonal matrices, the order doesn't matter, right? So, because in the diagonal matrices, if I have two diagonal matrices, I don't know, let's say A1, A2, AN, and I multiply B1, Bn, this is diagonal, everything else 0. Okay. What will be the product? It will be simply the product A1, B1, A2, B2. These are just ordinary numbers, right? It doesn't matter whether, if I change the order, it doesn't matter. So diagonal matrices always commute. So I could choose, for example, lambda 3 and lambda 8. But so certainly this will be an abelian subalgebra. That is clear, right? So lambda, if I look at the space generated by two-dimensional space generated by lambda 3 and lambda 8, by that what I mean that an arbitrary element will be some x lambda 3 plus y lambda 8, arbitrary element. It's a vector space. Now this clearly is an abelian subalgebra because they commute. But now the Kartha is not just an abelian subalgebra, it is a maximal abelian subalgebra. Meaning you cannot put anything more on that. If you put anything more on that inside this, it will no longer be abelian. And that you can easily see. You cannot put, you see, you can try to see if you put this guy or that guy, clearly it doesn't commute with this, right? If you put this guy, all these guys, it will not commute with that. Okay?
When we define the algebra,
Yeah.
we said that it should be closed under the commutation relation.
Yes.
So, but when we take the commutation relation to lambda 3 and lambda 8, it's does not belong to the
0 is always. This is the x equal to y equal to 0. I mean, in a vector space, 0 is always there. Right? 0 is always there.
So, not the generator should satisfy the.
I mean, what are we saying? The algebra means if I have x and y belongs to G, G being is a vector space. Huh? Vector space means what? I mean, if x and y are belonging to G, then any ax plus by also belongs to G for all a and b. Real, let's say real or complex depending on a vector space. Let's take real here. Real. Okay. So in particular, a equal to b equal to 0 is also a real numbers. So 0 is always an element of vector space. There's nothing. Now what we are saying is that the commutator of x, y belongs to G. So it is an element of this type. I mean, if it's two-dimensional. Suppose my vector space was two-dimensional. But in general, I mean, if I have some basis, I choose xi as a basis, then all that, what we are saying is that arbitrary vector of G, it would be some coefficients ai xi, summed over I. Right? Where ai's are arbitrary numbers. Ai's are, let's say, real numbers or even complex numbers. In fact, we'll be always talking about complexification, so complex numbers. So in particular, all the ai is equal to 0 is possible, is allowed, right? It's a vector space. No notion of adding and subtracting and so on. And all we are saying is that xi with xj will again be in G for all I and j. That's what it is.
Not in the generators. Not the generators are not close in between each other.
No. I mean, it's in the vector space. Yeah. It should be always possible to write it as some linear combination of the basis vectors. You choose some basis and take the commutator of two guys. It should be again a linear combination of the basis generators. But that coefficients may be 0. That's not a problem. Okay. So these two, lambda 3 and lambda 8, certainly is abelian. Abelian is a subalgebra. I mean, if I can find anything abelian, that's always subalgebra, of course. In abelian subspace, it's always subalgebra. But what is more, it is a maximum. It is a maximum. Because I cannot add to this anything else. Anything else I add, it's not going to commute with both of these guys. Right? It may commute with one of them, but not both. So, for example, some of these guys will commute. Let's see. Yeah, I mean, this guy, for example, would commute with this, with lambda 8. Because you see the 2 by 2 block here is identity. No? Others are 0 anyway. Third block is third row and third column is 0. So it doesn't care about that. Right? It only cares about this 2 by 2 block. But as far as 2 by 2 block is concerned, it's identity. So it will commute. So the lambda 2 and lambda 3 will commute with that. But they don't commute with this. No? So this is the maximum. And therefore, this is the Kartha subalgebra. Therefore, this is the Kartha subalgebra. I mean, there's nothing unique about Kartha's algebra. Just like in SU2, instead of sigma 3, I could have chosen sigma 1. No? But you can choose one of them. The properties will not change. The same kind of structures you will find. Kartha's algebra is this. Okay, now the next step is to find the like sigma plus and sigma minus, raising and lowering operators. We want to do that. So in other words, what does it mean? Remember in SU2 what we did? We chose sigma 3, and the other combinations we could construct sigma plus minus, which was sigma 1 plus minus I sigma 2. They had the property that this was again proportional to sigma plus minus with some numbers. Right? Those numbers plus was actually in that case it was simply plus minus. Actually no, it was a half, maybe plus minus 2. Anyway. Okay. But it was some number times itself. So that's the eigen. It's like the eigenfunction, right? So we are talking about this is the adjoint representation for sigma 3, and we are saying that sigma plus and sigma minus are the eigenstates of the adjoint representation. So what we want to do is we want to we have this maximal set, and we know that they can be simultaneously diagonalized. Okay, so we want to find all the other combinations which are eigenstates of the adjoint representations. Right? Well, so let me just write the answer, and then maybe you can check it again. And for this purpose, I will choose, instead of choosing this, lambda 3 and lambda 8 is at 8 as the basis, I will choose the basis, and let me use the same notation here. H1. Yeah. So we'll choose. We'll choose the basis H1, which is E11 minus E22. This is the same as lambda 3. But H2, I will choose to be E22 minus E33. You see? Yeah, E22 minus E33, which was one of those combinations. I think this was the same as root 3 lambda 8 minus lambda 1. I think by 2. Yeah, that combination, which had just the E22. So this was 0, 1, minus 1, everything else 0. Okay. This is fine. I can choose this basis, or I could choose lambda 3, lambda 8 basis. Doesn't matter. It's the same. It's a basis for that vector space, the Kartha's algebra. And then you can show. So let's just check for a few of them, and then I'll just write the answer. So the combination, which is not again from the SU2 experience, you already know what it should be. If I just focus on the SU2, what did we do? So you remember sigma 3 was my Kartha, which was 1 minus 1 0 0, and sigma 1 was 0 1 1 0. Sigma 2 was 0 minus I 0. Right? The combinations were sigma 1 plus I sigma 2 and sigma 1 minus I sigma 2. Now, what is special about it? You see, the special about it is if I add that up, what will happen? This will become 0, perhaps 2. Maybe I divide by half. That's not important. 0 2 0 0. Right? Because when I multiply by I, here becomes minus, and when I add it up, this cancels. So it's an upper triangular matrix. It's a purely upper triangular. See, lower block is all 0. It's only the upper which is not 0. Same thing here. It's the other way around. It's the lower one. This will become 0 2 0 0. So this is upper block, upper triangular, strictly upper triangular. Nothing diagonal is all 0. Upper triangular. And this is lower triangular. So this is the idea. So this is what we will do. So now if you look at this combination, for example, let's say these two combinations, these are exactly like sigma 2 and sigma 1. This and that. If I look at that, exactly sigma 1 and sigma 2. I will again take this combination. So lambda 1 plus I lambda 2 and lambda 1 minus I lambda 2. That will make it, one of them will be upper triangular, other will be lower triangular. Same thing you can do with this guy and this guy. If I take this plus or minus I times that, it will become again upper or lower triangular. And same thing will between this and this. Okay. So at the end, by choosing a combination, so if I write down these combinations, so what is it, lambda 1 plus I lambda 2, and then we had lambda 3, lambda 4 plus I lambda 5, and lambda 6 plus I lambda 7. All of these guys, this will be 0, 1, 0, 0, 0, 0, 0, 0. And this will be 0, 0, I think it's 1. Yeah, 1, 0, 0, 0, 0. And this will be 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay. And if you do the minus sign, it will be just a transpose of this. It will just become lower triangular. So, and such, yeah, I mean, so this is, of course, it's guaranteed, right? I mean, you see, our Cartan matrices are of the form, these are the Cartan matrices, right? Now, if you look at commutation relation of these matrices, IJ, KL. Suppose I look at this commutation relation. The EIJ, remember the matrix we defined, it is an n by n matrix, such that only non-zero element is in the ith row and jth column, right? Which is 1, we put it to be 1, and everywhere else 0. And same thing here, only non-zero is kth row and lth column. Now, so what will this be? Let's try to think about it. So in the matrix multiplication, what do? I take this matrix, so let's look at the disorder first, Eij times EKL. So I take this matrix, each row I multiply to each column here, right? Now the only time, if the row is not the ith row, this is 0 anyway, right? So the only possibly non-zero term will be in the ith row. So I'm just writing separately the two terms. So Eij, I'm multiplying it like this, Eij, EKL. Now, whatever it's going to be, we know that when I multiply any row, I mean, only the ith row, it possibly can be non-zero. Otherwise, it will all be 0, right? Because Eij, if the row is not ith, then it's all 0. So when I multiply that to any column, it's going to be 0, right? So at best, in the ith row, whatever the ith row is, it might not be 0, right? Everywhere else it will be 0. Now what about, let's see, continue that. So ith row, and then you multiply, so now we are looking at this row, but the only non-zero element is the jth column, right? So, whereas on the other hand, this here, only the kth row is non-zero, correct? So it has to be delta jk, right? Because the only way, I mean, I'm saying that only jth row is possibly non-zero, whereas there only kth row is non-zero. So it has to be proportional to delta jk, right? But then, even then, when will it be non-zero? Only in the ith row and lth column, right? So it's going to be, and it will be just 1. So it's going to be delta jk times EIL. Now, if I do other way around, so one can write it down exactly now here, delta jk EIL, and minus, now other way around, so it will be delta IL, let's say, times E, so L, kj, right? Kj. That's a computation relation. If you're not convinced, just try to write it down. I mean, maybe 3 by 3 matrix, and just try to see if you get this structure. The Kronecker delta times one of the basis element itself, matrix. No? It's going to be a matrix, so since I can express any matrix in terms of this basis, I'm just writing that. And try that. I mean, it will be useful to just try that. But if so, I mean, this is a property. Now, if you look at, let's specialize to the case. I mean, these guys are just involving only the EII type of objects, E11, E22, etc., etc. So we are looking at now something like EII. And this is something, this could be anything, EKL. If I look at this computation relation, what am I going to get here? Delta IK, so J is become I, no? So IK EIL minus delta IL, J has become I, no? L, EKI. So you see, this is again proportional to, I mean, the only time it will be non-zero is when I is equal to K. Okay? So, if at all it is non-zero, meaning if I happens to be equal to K, it is going to be give you back EKL. Okay? And similarly here, the only time it can be non-zero is if I is equal to L. So whatever it is going to be some number times EKL. The number could be 0. But whatever it is going to be proportional to EKL. Okay. So it's telling you that EKL is already going to be an eigenstate. Yeah? That's the point. So it is enough to just choose one of these. I mean, if I have just EKL, so just a matrix with, this, like such a matrix. Here there's only, this is just E12, nothing else. This guy is E13 in our notation, E13. This is E23. Okay. So when I take the commutation relations with these kinds of objects, E11, E22, or these combinations, whatever I'm going to get on the right hand side will be again proportional to E12, or E13 in this case, or E23 in that case, which means they're going to be eigenstates, right? So all you need to compute is numbers. These numbers will tell me what is the eigenvalue. Those will be different. For different choices, they'll be different. Right? And it depends on whether you take H1 or H2. Right? H1 will have some eigenvalue, H2 will have some eigenvalue. And these eigenvalues are summarized in this way. And this is again, please check it. Because if I have to do this in the blackboard, it just takes unnecessary time for no particular reason. So these are called the roots. So you look at, you define something like this. So these are my HI, whatever the basis I've chosen. So HI, the commutator of HI with some eigenstate. So actually what I'm claiming is that these are the eigenstates. But in general, now I'm talking about in general, some combinations of the remaining guys, not the Karta, but the remaining guys, I call, this is my just a notation, alpha I, and that's equal to, let's see, no, so just call it X alpha, then this is alpha I X alpha. So what we are saying is these are eigenstates with the eigenvalue alpha I. So for H1 it will be alpha 1, H2, this is not the notation, sorry, I should say, no, what shall I call? Again, I think there's a typo in the last expression because we are using the index in the wrong way. What shall I call? Let me just put no index here, H. And here I am putting some index A. Let's put here some index A because there are different eigenstates. I mean, there are all these different eigenstates. I have to label them somehow, right? So let's say this one is x1, this one is x2, this x3, and then the minus signs will give you, three different guys. So I have to label them somehow. Okay. So this is just labeling them. So I have 6 of them in the case of SU3, right? 6 of them, and the eigenstates, eigenfunction I write like that. Alpha A, HI, X alpha. So what does it mean, this notation? So this is just labeling. This is just labeling the remaining guys. And this is telling you that this particular guy will have some eigenvalue, and that eigenvalue will depend on which HI you are looking at, right? They will be different this will have carry different eigenvalue, this will be carry different eigenvalue. Let's just compute it once. So if I look at H11 and I look at this guy, E12, maybe it's better to just do it one or two examples explicitly. So E12, I want to look at the commutation relation of E12 with say H1. Okay, so I do that. So H1 was, remember, well, I mean, we already had this formula, but anyway, H1 is just that, lambda 3. Okay? H1 was lambda 3, which is E11 minus E1. So I look at this, I'm going to get 2 E12. 2 because I didn't divide by 2. I mean, unlike in the SU2 case, we are dividing by 2. That's to get that. On the other hand, if you look at the H2 and look at the thing, then it's not going to give me anything. You see, it's going to give me a 0. Right? Because, oh no, not H1, sorry, no, not true. Then I get confused with the lambda 8. If you now look at the H2, so we can see, what is this one? This one is 0, 1, minus 1, 0, 0. And this object E12 was that 0, 1, 0, 0, 0, 0, 0, 0, 0. So if I multiply like this, it is all 0. But if I do other way, so this is 0. This is 0 matrix. But if I do other way, 0, 1, 0, 0, 0, 0, 0, 0, 0, because I have to take the commutator, no? 0, 0, 1, 0. Now there's a term, this times that. Okay? So it's going to be the first 1, 2 element, 0, 1, 0, 0, 0, 0. Okay? But since I have to subtract here, right, when I take the commutator, I have to take this minus that. So you will get. So therefore we see that H2 with E12, commutator will be minus E12. So this notation is this. So this is just the labeling. So for say 1, 2, similarly there will be 1, 3 and all that. This is the labeling that. And this tells you that what is its eigenvalue with respect to H1 and H2. So in this case it will be 2 and minus 1. Okay. So there is this form, I mean actually this is exercise 8.4. You can check that. Try to see that all these numbers are right. It gives the eigenvalues of those. Yeah, so I think I'll stop now. Tomorrow we'll continue. But this is the thing, this is the basic thing, this is the way we're going to understand this. Taking different SU2 subalgebras and work out. So here, yeah, I mean, we will see now. This, when you look at this eigenvalues, it's clearly, I mean, very nicely classified into 3 different SU2 subalgebras sitting inside SU3. Yeah, because there are 2 eigenvalues here. So they have 2, H1 and H2. You have to plot eigenvalues in a 2-dimensional plane. Unlike in the SU2 case, it was just the m quantum number. It was just going in integer units in one line. But now we have 2 independent things. So you have to draw. Okay. So any question?
The structural constants depend on the basis we choose.
On the basis, yeah.
But there is a rule to get these structural constants if we go to higher dimension limits. There is a rule to get them.
You have to always choose some basis. Otherwise, because the structure constant are explicitly those indices, no? Indices means you are choosing some basis.
Yeah.
But there are I mean there are standard ways. Yeah, you can. Yeah, you can construct. You can choose some kind of. Your question is whether there is a pattern in choosing this.
Yes.
There are patterns. I mean, for all the classical groups, I mean SUs, SO, or symplectic. Symplectic, I haven't started talking about it, but it's like you must have seen in the Hamiltonian mechanics. No, there are this notion of canonical transformations, momenta and coordinates getting mixed up. So that's again another symmetry, important symmetry group which appears in physics in general. Yeah, in all of them there is a kind of systematic way. There's some pattern that repeats for all the n's, sp, n. Okay, so see you tomorrow.
y, x.